natural world has a peculiar way of humbling even the brightest minds among us. Throughout the history of scientific discovery, there have been moments when nature has pulled the wool over our collective eyes, leading researchers down paths of investigation that would ultimately reveal something entirely different from what they initially believed. These instances serve as powerful reminders that observation, no matter how careful, can sometimes deceive us, and that the truth often lies hidden beneath layers of complexity that take decades or even centuries to unravel. One of the most fascinating cases of scientific misdirection involves a creature that baffled zoologists for nearly 2 centuries. The platypus, that peculiar Australian mammal with its duckbill, beaver tail, and venomous spurs, caused such confusion when specimens first arrived in Europe that scientists initially dismissed it as an elaborate hoax. In 1799, when the first preserved platypus specimen reached England, naturalists examining it believed they were looking at a taxidermy fraud, something cobbled together from various animal parts as a joke or an attempt to fool the scientific establishment. George Shaw, the British naturalist who first described the creature, was so skeptical that he took scissors to the dried skin, searching for stitches that would reveal the deception. He found none, because there were none to find. But the confusion was only beginning. For decades, scientists debated the basic biological classification of this creature. It had fur like a mammal, but it laid eggs like a reptile. It had mammary glands, yet no nipples, with milk instead oozing through pores in the skin. Early naturalists struggled to place it within their understanding of the animal kingdom. Some suggested it might be an evolutionary link between different classes of animals. Others proposed it represented an entirely separate branch of life. The debates grew heated, with reputations staked on competing theories about where this animal fit in the natural order. The mystery deepened when researchers began studying platypus reproduction. In the 1820s and 30s, scientists observed pregnant female platypuses, but could not definitively prove whether they laid eggs or gave birth to live young. Indigenous Australian peoples had long known that platypuses laid eggs, but European scientists dismissed these accounts, unable to reconcile egg-laying with the presence of mammary glands. It was not until 1884, nearly a century after the first specimen reached Europe, that a young Scottish scientist named William Caldwell finally confirmed that platypuses did indeed lay eggs. He sent a telegram back to the British Association for the Advancement of Science with the simple message that would resolve decades of debate. Even then, many in the scientific community initially refused to believe his findings. What makes the platypus story so remarkable is not just the length of time scientists remained fooled, but the fundamental assumptions that prevented them from accepting the truth. The prevailing understanding of mammalian biology was so rigid that evidence contradicting it was automatically suspect. Scientists had constructed a framework for understanding animal classification that seemed comprehensive and logical, and the platypus simply did not fit. Rather than adjusting the framework, many chose to doubt the animal itself. The platypus was not alone in causing such prolonged confusion. Another creature that mystified researchers for an astonishing length of time was the barnacle. These small crustaceans that attach themselves to rocks, ships, and other surfaces in marine environments seem unremarkable today. But for centuries, naturalists had absolutely no idea what they were. The prevailing theory, which persisted from medieval times well into the 19th century, was that barnacles were not animals at all, but rather a type of plant or fungus that spontaneously generated from driftwood and other debris in the ocean. This belief was so deeply entrenched that it gave rise to an even more bizarre theory. Because certain types of barnacles, specifically goose barnacles, were often found attached to driftwood that had been at sea for long periods. And because these barnacles had a superficial resemblance to the neck of a goose, scholars in medieval Europe concluded that geese literally grew from these barnacles. The theory held that certain species of geese, particularly the barnacle goose, did not hatch from eggs like other birds, but instead developed from these marine organisms. This belief was not relegated to folklore or superstition, but was widely accepted by learned scholars and appeared in serious scientific texts. The implications of this theory were far-reaching and sometimes absurd. Since barnacle geese were believed to come from the sea rather than from eggs laid by birds, some Catholic authorities argued that they could be classified as fish and therefore eaten during Lent, when the consumption of meat was forbidden. This culinary loophole remained a subject of debate well into the Renaissance. The theory persisted because the actual breeding grounds of barnacle geese, which migrate to remote areas of the Arctic to nest, were unknown to Europeans. No one had actually observed these birds laying eggs or raising young, so the barnacle theory, however strange, filled an observational gap. It was not until the 19th century that scientists finally understood that barnacles were crustaceans related to crabs and shrimp, rather than plants or some bizarre progenitor of birds. The key breakthrough came through the study of barnacle larvae, which look nothing like the sessile adults. Young barnacles swim freely in the ocean before eventually settling on a surface and transforming into the familiar armored forms that cover rocky shores. This metamorphosis was so complete that early naturalists, examining only adult barnacles, had no way of connecting them to their larval forms or understanding their true nature. The misidentification persisted for so long because scientists were looking at only part of the life cycle and making assumptions based on incomplete information. The story of barnacles reveals how easily scientific understanding can be derailed by superficial observations and the human tendency to construct narratives that fit existing beliefs. For centuries, otherwise rational scholars accepted the goose barnacle theory, not because the evidence was compelling, but because it provided an explanation for observations that otherwise had no answer. Once the theory became established, it took on a life of its own, cited by successive generations of scholars who never thought to question it rigorously. An equally lengthy deception involved the question of where birds went during winter. Today, we understand bird migration as a routine biological phenomenon, but for much of human history, the seasonal disappearance of certain bird species was a profound mystery that generated wildly incorrect theories. Ancient Greek philosophers like Aristotle proposed that birds transmuted into different species with the changing seasons, or that they hibernated in caves or hollow trees. Some scholars suggested that swallows, which disappeared from Europe each autumn, actually dove into ponds and lakes to spend the winter underwater in a state of suspended animation. This aquatic hibernation theory for swallows persisted with remarkable tenacity well into the 18th century. Fishermen occasionally reported finding torpid birds in the mud at the bottom of drained ponds, which seemed to confirm the theory. In reality, these were likely sick or dying birds that had fallen into the water, but the observations were interpreted through the lens of the prevailing theory. Respected naturalists, including Carl Linnaeus, the father of modern taxonomy, gave credence to the idea of underwater bird hibernation. The theory appeared in scientific literature and was taught as fact. Other proposed explanations for the disappearance of birds were equally creative. Some theorists suggested that birds flew to the moon for the winter, a journey that would take months and explain why they were gone so long. This lunar migration theory addressed the apparent problem that no one had ever identified a place on Earth where these birds spent their winters, so perhaps they were not on Earth at all. The theory conveniently ignored the challenges of breathing in the upper atmosphere or surviving in the vacuum of space. But in an era before aviation or space exploration, these were not obvious objections. The truth about bird migration began to emerge slowly through careful observation and record-keeping. By the 18th century, some naturalists were tracking the movements of bird species across continents and beginning to piece together migration routes. But definitive proof remained elusive until technology advanced enough to mark individual birds and track their journeys. The practice of bird banding, attaching small numbered metal rings to birds' legs, began in the early 20th century and finally provided irrefutable evidence of long-distance migration. Birds banded in northern Europe were recovered in southern Africa, proving that the same individual birds traveled thousands of miles between summer and winter grounds. What makes the bird migration confusion particularly instructive is that the truth was actually quite accessible. Ancient peoples in various parts of the world, including those living along migration routes, understood that birds moved with the seasons. The problem was not a lack of evidence, but rather a failure of communication and a preference for exotic theories over mundane explanations. European scholars, convinced that they were uncovering nature's deepest secrets, overlooked simple observations that would have pointed them in the right direction. A similar pattern of prolonged confusion based on incomplete observation occurred with the eel. These snake-like fish have a complex life cycle that remained mysterious until the 20th century. And for thousands of years, the question of how eels reproduced was one of the great unsolved puzzles of natural history. The ancient Greek philosopher Aristotle, who made careful observations of many animal species, concluded that eels spontaneously generated from mud. He noted that eels had no visible reproductive organs and that no one had ever observed eel eggs or mating behavior. His conclusion, while wrong, was not unreasonable given the evidence available to him. This extraordinary life cycle was not definitively proven until the early 20th century. A Danish oceanographer named Johannes Schmidt spent years tracking eel larvae across the Atlantic, gradually narrowing down the spawning location. Even after he identified the Sargasso Sea as the breeding ground in 1922, some scientists remained skeptical. The spawning grounds are in such deep water that adult eels had never been directly observed breeding, even with modern technology. The full details of eel reproduction remain incompletely understood even today, though the basic outlines are now established beyond doubt. The eel story demonstrates how a mystery can persist, not because evidence is entirely lacking, but because the true explanation is so far removed from ordinary experience that it lies outside the realm of reasonable speculation. For millennia, naturalists searched for eel reproduction in rivers and ponds, never imagining that the answer lay thousands of miles away in the middle of the ocean. The assumptions about where to look prevented the discovery of where eels actually went. Turning from animals to plants, we find another case of prolonged scientific confusion in the mystery of plant nutrition. Today, we learn in elementary school that plants create their own food through photosynthesis, using sunlight, water, and carbon dioxide to produce sugars. But this understanding is relatively recent, and for centuries, scientists were completely wrong about how plants obtained the nutrients they needed to grow. The prevailing theory, which dominated from ancient times through the 17th century, held that plants ate soil. This soil consumption theory seemed logical based on simple observation. When you plant a seed in soil, a plant grows. The plant gets bigger and bigger, adding substantial mass. The soil in the pot or garden bed seems to decrease slightly as it is disturbed by roots. The conclusion appeared obvious. The plant was consuming the soil and converting it into plant tissue. Supporting this theory was the observation that different soils produced different growth results. Rich, dark soils yielded healthy plants, while poor, sandy soils produced stunted growth. Clearly, the quality of the soil mattered, because that was what the plant was eating. This theory faced a significant challenge in the 17th century, when a Flemish chemist named Jan Baptist van Helmont conducted a famous experiment. He planted a small willow tree in a pot containing a measured amount of soil, then watered it regularly for 5 years. At the end of this period, he carefully removed the tree and weighed both it and the soil. The tree had gained about 164 pounds, while the soil had lost only 2 ounces. Van Helmont concluded that the tree's mass must have come almost entirely from the water he had added, not from the soil. Van Helmont's conclusion was closer to the truth than the soil consumption theory, but it was still incomplete. Water does provide the hydrogen and oxygen atoms that become part of plant tissue, but it does not account for all of a plant's mass, particularly the carbon that makes up much of the structure of leaves, stems, and roots. The full answer would not come until scientists understood the composition of air and the chemical processes occurring in leaves. The key breakthrough came in the 18th century, as chemists began identifying the different gases that make up the atmosphere. Joseph Priestley, an English chemist, discovered that plants had a curious effect on air. He found that a mint plant growing in a sealed container could restore air that had been depleted by a burning candle or a breathing mouse. Somehow, the plant was changing the air in a way that made it breathable again. We now understand he was observing oxygen production during photosynthesis, but at the time, the mechanism was completely mysterious. Later experiments by Jan Ingenhousz demonstrated that this air-purifying effect only occurred in the presence of sunlight, and that it was specifically the green parts of plants that produced it. Finally, Swiss scientist Nicolas Théodore de Saussure showed that plants absorbed carbon dioxide from the air during this process. Gradually, piece by piece, scientists assembled the puzzle of photosynthesis, realizing that plants were essentially eating air, combining carbon dioxide from the atmosphere with water from the soil to create sugars, releasing oxygen as a byproduct. This revelation was revolutionary because it meant that the visible, physical substance of plants, the wood and leaves and flowers, was being constructed primarily from an invisible gas. The ancient trees in a forest are built mostly from air, transformed through the alchemy of photosynthesis into solid matter. For centuries, scholars had been looking in the wrong place, focused on the soil beneath the plants, when the real source of plant nutrition was floating all around them. The delay in understanding photosynthesis was partly due to the fundamental difficulty of observing and measuring gases, which were poorly understood until the development of modern chemistry. But it was also due to the compelling nature of the wrong theory. Soil consumption made intuitive sense and fit with everyday observations. The correct explanation required understanding processes and substances that were invisible to the naked eye, and whose existence was not even suspected until relatively recently in human history. Another botanical mystery that fooled scientists for an extended period concerned the nature of fossils. Today, we understand fossils as the preserved remains or traces of ancient organisms, but for much of history, the true origin of fossils was hotly debated. Fossils of marine creatures found on mountaintops or far from any ocean were particularly puzzling. How did seashells end up embedded in rocks at high elevations, often hundreds of miles from the nearest coast? Various theories emerged to explain these inconvenient observations. Some scholars proposed that fossils were merely rock formations that coincidentally resembled living creatures, formed by minerals crystallizing into lifelike shapes. This theory held that fossils had never been alive at all, but were simply natura ludens, nature playing games, creating forms that mimicked life without actually being derived from it. Others suggested that fossils were the remains of creatures that had died in the Great Flood, described in the biblical book of Genesis, with Noah's deluge scattering marine creatures across the landscape as the waters receded. The flood theory had particular staying power because it seemed to reconcile geological observations with religious texts. If a worldwide flood had occurred, it would explain both the presence of marine fossils far from oceans and the fact that similar fossils could be found on different continents. The theory was supported by respected scientists well into the 19th century, despite growing evidence that it could not account for all observations. The geological layers containing fossils were far too extensive and varied to be explained by a single flood event, and the vertical distribution of different fossil types in the rock record suggested a long sequence of depositions, not a single catastrophic inundation. The correct explanation for marine fossils on mountains involves the movement of tectonic plates and the uplift of ancient seabeds. Rocks that formed at the bottom of oceans millions of years ago have been pushed up by geological forces to form mountain ranges. The Himalayas, the highest mountains on Earth, contain fossils of marine creatures because the rock that makes up these peaks was once at the bottom of an ancient ocean called the Tethys Sea. The collision between the Indian and Asian tectonic plates compressed and uplifted the seafloor, creating the mountain range. This understanding required the development of the theory of plate tectonics, which was not widely accepted until the 1960s. For centuries before that, scientists had no framework for understanding how rocks could move vertically over such vast distances. The processes of mountain building operate so slowly, at rates of inches per year or less, that they are imperceptible within a human lifetime, or even within recorded history. Without understanding these processes, the presence of marine fossils at high elevations seemed inexplicable, leading to creative but incorrect theories. The fossil debate also involved deeper questions about the age of the Earth. Biblical scholars in the 17th century calculated that the Earth was only about 6,000 years old, based on genealogies and timelines in religious texts. This timeline did not allow enough time for the slow processes of sedimentation, fossilization, and mountain building that geologists were beginning to recognize. As geological evidence accumulated, it became clear that the Earth had to be far older than a few thousand years. But accepting this conclusion required abandoning or reinterpreting long-held religious beliefs about creation. The conflict between geological evidence and religious chronology was not easily resolved. Even scientists who recognized that the Earth must be ancient struggled to estimate its actual age. Early estimates in the 19th century ranged from millions to hundreds of millions of years. But the true age, approximately 4.5 billion years, was not established until the 20th century, with the development of radiometric dating techniques. For generations, scientists knew that previous estimates of Earth's age were wrong, but could not determine the correct answer with confidence. Moving into the realm of physics, we find another case of prolonged scientific misdirection in the story of phlogiston. In the 17th and 18th centuries, scientists studying combustion and respiration developed a theory to explain these processes. They proposed that all flammable materials contained a substance called phlogiston, which was released during burning. When wood burned or metal rusted, they were releasing their phlogiston into the air. Conversely, when metal ores were smelted into pure metal, they were absorbing phlogiston from the charcoal used in the smelting process. The phlogiston theory was remarkably successful at explaining a wide range of observations. It accounted for why fires went out in sealed containers. The air became saturated with phlogiston and could not absorb any more, preventing further combustion. It explained why some materials burned better than others. They contained more phlogiston. It even explained certain aspects of respiration, which was viewed as a slow form of combustion occurring in the body. For about a century, phlogiston theory was the dominant explanation for combustion, accepted by virtually all chemists and taught in universities across Europe. The problem was that phlogiston did not exist. The processes scientists were observing involved oxygen, but the role of oxygen in combustion and respiration was not understood until the late 18th century. The breakthrough came through careful weighing experiments that revealed a fatal flaw in phlogiston theory. When metals rusted, they gained weight rather than losing it, which was difficult to explain if rusting involved the release of phlogiston. According to the theory, losing phlogiston should make materials lighter, not heavier. French chemist Antoine Lavoisier conducted meticulous experiments in the 1770s and 1780s, showing that combustion and rusting involved the combination of materials with a component of air, which he named oxygen. When wood burned or metal rusted, they were not releasing phlogiston, but rather combining with oxygen from the atmosphere. This explained the weight gain observed in rusting metals. They were absorbing oxygen atoms and thus becoming heavier. Lavoisier's work essentially founded modern chemistry, establishing the principle of conservation of mass and demonstrating the importance of quantitative measurements in chemical experiments. Despite Lavoisier's compelling evidence, phlogiston theory did not disappear immediately. Many chemists had invested their careers in the phlogiston framework and were reluctant to abandon it. Defenders of the theory proposed modifications to account for the weight discrepancies, suggesting that phlogiston might have negative weight or that other factors were at play. The debate continued for years, with some chemists maintaining their belief in phlogiston well into the 19th century, decades after it had been definitively disproven. The persistence of phlogiston theory illustrates how scientific paradigms can continue to exert influence even after evidence against them accumulates. Scientists become invested in particular explanations, not just intellectually, but also professionally and emotionally. Admitting that a central theory is completely wrong means acknowledging that years of work may have been misdirected. This natural human reluctance to accept paradigm shifts can delay scientific progress, sometimes for generations. In the field of medicine, perhaps no misconception lasted longer or caused more harm than the theory of the four humors. Ancient Greek physicians, particularly Hippocrates and later Galen, developed a theory that the human body contained four fundamental fluids or humors: blood, phlegm, yellow bile, and black bile. Health was thought to result from these humors being in proper balance, while disease occurred when they became unbalanced. Different personality types were also attributed to the predominance of particular humors, giving us terms like sanguine, phlegmatic, choleric, and melancholic that are still used today. The theory of humors dominated Western medicine for over 2,000 years, from ancient Greece through the Middle Ages and well into the modern era. Medical treatment was designed to restore humoral balance, often through methods that seem bizarre and dangerous today. Bloodletting, the practice of deliberately draining blood from patients, was the most common medical procedure for centuries, based on the belief that many diseases involved an excess of blood that needed to be removed. Physicians would open veins or apply leeches to draw out blood, sometimes removing quantities that would leave patients weak and anemic. Other treatments based on humoral theory included purging, inducing vomiting or diarrhea to expel excess bile, and various dietary restrictions designed to balance the humors. Hot foods were prescribed to counter cold humors, dry foods to counter wet humors, and so on. The system was comprehensive and internally consistent, providing an explanation for virtually any symptom or disease. Its very completeness made it intellectually satisfying and difficult to challenge. The problem was that humoral theory was completely wrong. Black bile does not exist as a distinct bodily fluid. The humors do not need to be balanced because they do not govern health in the way the theory proposed. Bloodletting does not cure disease. In most cases, it makes patients worse by weakening them when they most need their strength. Yet the theory persisted because it provided a framework that seemed to work. Patients sometimes recovered after humoral treatments, not because the treatments were effective, but because many illnesses resolve on their own given time. These spontaneous recoveries were credited to the treatment, reinforcing belief in the underlying theory. The gradual abandonment of humoral theory came only with the development of modern medicine in the 19th and 20th centuries. The discovery of microorganisms as causes of disease, the understanding of how the circulatory and immune systems actually function, and the development of effective treatments based on correct models of physiology, all of these advances made humoral theory obsolete. But the transition was slow and uneven. Bloodletting continued to be practiced in some places into the early 20th century, and remnants of humoral thinking persisted in folk medicine even longer. The longevity of humoral theory reveals something important about the nature of scientific error. A wrong theory can survive for centuries if it is comprehensive, if it provides explanations for many observations, and if it is embedded in authoritative texts that are widely taught and respected. The theory does not need to be correct to be persuasive. It merely needs to be plausible and to fit within the broader intellectual framework of its time. Another medical mystery that confused scientists involves the transmission of diseases. Before the development of germ theory in the 19th century, the causes of infectious diseases were poorly understood, and various incorrect theories competed for acceptance. One of the most influential was the miasma theory, which held that diseases were caused by bad air or noxious vapors rising from decaying organic matter. According to this theory, malaria, literally bad air in Italian, was contracted by breathing the putrid exhalations from swamps. Cholera, plague, and other epidemic diseases were likewise attributed to miasmas. The miasma theory seemed to explain many observations. Cities with poor sanitation, where garbage and human waste accumulated in the streets, did indeed have higher rates of disease. Areas near swamps and stagnant water were unhealthy. The theory led to some beneficial public health measures, such as improving urban sanitation and draining swamps, which did reduce disease, even though the theory underlying these measures was wrong. The improvements worked not because they eliminated miasmas, but because they removed breeding grounds for mosquitoes and reduced contamination of water supplies with disease-causing organisms. The correct explanation for infectious diseases, that they are caused by microscopic organisms that pass from person to person or through contaminated water and food, was proposed by various scientists in the 19th century, but faced significant resistance. When English physician John Snow traced an outbreak of cholera in London in 1854 to a contaminated water pump, his careful epidemiological work was dismissed by many authorities who remained convinced that cholera spread through bad air. Snow's demonstration that removing the handle from the infected pump stopped the outbreak was compelling evidence, but it took decades for germ theory to become widely accepted. The resistance to germ theory came partly from the fact that the organisms supposedly causing disease were invisible to the naked eye. Accepting their existence required trusting in microscopes and in the observations of scientists who claimed to see tiny creatures in water and other substances. For physicians trained in miasma theory, or other established frameworks. The idea that invisible animalcules could cause devastating epidemics seemed far-fetched. The theory also implied that physicians might be spreading diseases themselves if they failed to maintain proper hygiene, a suggestion that many doctors found insulting. The definitive proof of germ theory came through the work of Louis Pasteur and Robert Koch in the latter half of the 19th century. Pasteur demonstrated that microorganisms caused fermentation and spoilage, and that sterilization could prevent these processes. Koch developed methods for isolating and culturing specific bacteria, and proved that particular bacterial species caused specific diseases. Together, their work established the germ theory of disease beyond reasonable doubt, though full acceptance in the medical community took additional years. The transition from miasma theory to germ theory had profound practical consequences. Once doctors understood that diseases could be transmitted through contaminated instruments or unwashed hands, practices like surgical sterilization and hand washing became standard. These simple measures dramatically reduced infection rates and saved countless lives. Before germ theory, surgery was extraordinarily dangerous, with many patients dying from post-operative infections. The mortality rate from amputations in mid-19th century hospitals was often above 50%. After sterilization techniques were adopted, survival rates improved dramatically. In the realm of astronomy, scientists were fooled for centuries by the apparent rotation of the stars around the Earth. The geocentric model of the universe, which placed Earth at the center with the sun, moon, planets and stars all revolving around it, was the dominant cosmological framework from ancient times through the 16th century. This model was codified by the Greek astronomer Ptolemy in the 2nd century and became deeply embedded in both scientific and religious thought. The geocentric model seemed obviously correct, based on everyday observation. The sun rises in the east and sets in the west, appearing to circle the Earth. The stars wheel overhead at night in predictable patterns. The Earth feels stationary beneath our feet. To suggest that the Earth was actually spinning and orbiting the sun seemed to contradict direct sensory experience. Critics of the heliocentric model asked why, if the Earth was spinning, we did not feel a constant wind as the atmosphere rushed past us, or why objects thrown straight up did not land far to the west as the Earth rotated beneath them. These objections seemed reasonable before the development of modern physics and the understanding of inertia and relative motion. The atmosphere rotates with the Earth, so there is no relative motion between the air and the surface. Objects thrown upward carry the Earth's rotational motion with them, so they fall back to the same spot. These explanations were not available to ancient or medieval scholars, making the geocentric model the more intuitive choice. The heliocentric model, which correctly places the Sun at the center of the solar system, with the Earth and other planets orbiting it, was proposed by Greek astronomer Aristarchus as early as the 3rd century before the Common Era. But his ideas found little acceptance. The model was revived by Nicholas Copernicus in the 16th century and gradually gained support, despite fierce opposition. The Catholic Church condemned heliocentrism as heretical, and Galileo Galilei was tried by the Inquisition and placed under house arrest for advocating it. The transition from geocentric to heliocentric cosmology was not just a matter of correcting a scientific error. It represented a fundamental shift in humanity's understanding of its place in the universe. The geocentric model placed humans at the center of creation, with the heavens revolving around us. The heliocentric model demoted Earth to just another planet, orbiting an ordinary star in an unexceptional corner of space. This was philosophically and theologically threatening, in ways that went beyond scientific accuracy. Final proof of Earth's motion came gradually through various observations. The discovery that Venus shows phases like the Moon, which Galileo observed through his telescope, was difficult to explain in a geocentric framework, but natural in a heliocentric one. Measurements of stellar parallax, the apparent shift in position of nearby stars as Earth moves through its orbit, finally provided direct evidence of Earth's motion in the 19th century. By then, heliocentrism had been accepted by astronomers for over 2 centuries, but the empirical proof came late. Another astronomical misconception involved the Milky Way galaxy. Through much of the 20th century's early decades, astronomers debated whether the Milky Way constituted the entire universe or whether other galaxies existed beyond it. Some astronomers identified spiral nebulae, cloudy patches in the night sky with a distinctive spiral structure, but could not determine whether these were relatively nearby clouds of gas within our galaxy or separate galaxies far beyond it. The debate was known as the Great Debate and came to a head in 1920 when astronomers Harlow Shapley and Heber Curtis presented opposing views in a formal discussion. Shapley argued that the Milky Way was far larger than previously thought and that the spiral nebulae were part of it. Curtis contended that the spiral nebulae were separate island universes, as large as the Milky Way, but much farther away. The resolution came through improved observations by Edwin Hubble, who identified individual stars in the Andromeda Nebula and measured their brightness to determine distance. He proved that Andromeda was far too distant to be part of the Milky Way, confirming that it was a separate galaxy. This discovery dramatically expanded the known universe. The Milky Way, which had seemed to encompass all of existence, was revealed to be just one galaxy among countless others. Modern estimates suggest there are hundreds of billions of galaxies in the observable universe, each containing hundreds of billions of stars. The confusion about the scale of the universe persisted until the 1920s, simply because the distances involved were so vast that they exceeded the measuring capabilities of earlier instruments. In the field of psychology and neuroscience, scientists have been repeatedly fooled by assumptions about brain function. One long-standing misconception held that different parts of the brain operated independently, with specific functions strictly localized to particular regions. This modular view of the brain suggested that damage to one area would eliminate a specific function while leaving others intact. The reality is far more complex, with most cognitive functions depending on networks of brain regions working together. While certain areas do specialize in particular tasks, the brain shows remarkable plasticity, with functions sometimes relocating after injury. Another persistent myth claimed that humans use only 10% of their brains. This notion, which has no scientific basis, probably arose from misunderstandings of early neuroscience research. Brain imaging studies have conclusively shown that all areas of the brain show some level of activity over the course of a day, and even during specific tasks, far more than 10% of the brain is engaged. The myth persists in popular culture, despite being thoroughly debunked by neuroscientists. A more specific case of neuroscientific confusion involved the understanding of sleep and dreams. For much of the 20th century, sleep was viewed as a passive state, a time when the brain simply shut down to rest. The discovery of rapid eye movement sleep in 1953 revealed that sleep involves active brain processes, with some stages showing brain activity patterns similar to waking. Further research has shown that sleep serves crucial functions in memory consolidation, toxin removal from the brain, and various other restorative processes. Far from being dormant, the sleeping brain is engaged in complex activities essential for health. The purpose of dreams remains incompletely understood, but early theories about dreams were dramatically wrong. Freud's psychoanalytic interpretation viewed dreams as disguised representations of unconscious wishes, particularly repressed sexual desires. While Freud's work was influential in psychology more broadly, his specific theories about dream content have not held up to empirical scrutiny. Modern neuroscience suggests dreams may serve functions related to memory processing and emotional regulation. But the field acknowledges that much remains unknown about why we dream. In geology, scientists were fooled for decades by gradualism, the assumption that all geological change occurs slowly over vast time periods. While many geological processes are indeed slow, the discovery of catastrophic events like meteorite impacts and massive volcanic eruptions revealed that rapid changes can also shape the Earth's surface and history. The extinction of the dinosaurs, long attributed to gradual climate change or competition with mammals, is now understood to have resulted from a massive asteroid impact 66 million years ago. The evidence for this impact, including a global layer of iridium-rich sediment and the identification of the impact crater in Mexico, was not accepted until the 1980s, decades after it was first proposed. The gradualist bias in geology was partly a reaction against earlier catastrophist theories that attributed geological features to biblical floods and other supernatural events. In rejecting these religious explanations, geologists sometimes went too far in dismissing the possibility of any rapid changes. The truth, as often happens in science, lies in a middle ground. Earth's history involves both slow processes operating over millions of years and occasional catastrophic events that reshape the planet in moments. Another geological confusion involved the nature of the Earth's interior. In the 19th century, scientists debated whether the Earth was solid throughout or had a molten core. Some geologists argued that the Earth had formed as a molten ball and was gradually cooling, with a solid crust overlying liquid rock. Others contended that the entire Earth was solid, pointing to the fact that the Earth transmits certain types of seismic waves that cannot travel through liquids. The resolution came through more sophisticated seismic studies that revealed the Earth's layered structure: a solid inner core, liquid outer core, and solid mantle and crust. The presence of both solid and liquid layers had confused earlier interpretations of seismic data. In the biological sciences, the mechanism of heredity puzzled scientists until the 20th century. Gregor Mendel's work on inheritance in pea plants, published in 1866, went largely unnoticed for decades. Meanwhile, other scientists pursued incorrect theories of heredity. The concept of blending inheritance suggested that parental traits mixed together in offspring, like paints blending on a palette. This theory could not explain why traits sometimes skipped generations, or why traits did not become increasingly averaged over time. Even after Mendel's work was rediscovered in 1900 and became the foundation of genetics, scientists did not immediately connect it with Darwin's theory of evolution. Some biologists saw Mendelian genetics as contradicting Darwin, since Mendel described discrete traits, while Darwin emphasized continuous variation. The synthesis of genetics and evolutionary theory, showing how they complement rather than contradict each other, was not achieved until the 1930s and 40s. For decades, scientists failed to see the connections between different areas of biology because they were thinking in separate theoretical frameworks. The discovery of DNA's structure by Watson and Crick in 1953 is often portrayed as a sudden breakthrough, but it built on decades of work by other scientists whose contributions were overlooked. Rosalind Franklin's X-ray crystallography images were crucial to determining the double helix structure, but her role was minimized for years. The understanding that DNA carried genetic information had been established by earlier experiments that were not widely known. Scientific progress often involves many people making incremental contributions, but the narrative gets simplified into stories of individual genius and sudden breakthroughs. In chemistry, scientists were confused for generations about the nature of chemical bonds. Early theories described atoms as having hooks or arms that attached to other atoms, a crude but intuitive model. The development of quantum mechanics in the early 20th century revealed that chemical bonds involve the behavior of electrons in ways that have no analog in everyday experience. Electrons exist in probability clouds rather than fixed orbits, and chemical bonds involve the overlap of these clouds in ways that can only be described mathematically. The truth was far stranger than the mechanical model scientists had constructed. The periodic table of elements, now a fundamental organizing principle in chemistry, was initially met with skepticism when Dmitri Mendeleev proposed it in 1869. Mendeleev arranged elements by atomic weight and chemical properties, leaving gaps for elements not yet discovered, and even predicting the properties of these missing elements. When elements fitting his predictions were subsequently discovered, the periodic table gained acceptance. But Mendeleev did not understand why the table had the structure it did. The explanation came only with quantum mechanics and the understanding of electron shells, decades after Mendeleev's death. In the study of human origins, scientists have been repeatedly surprised by discoveries that contradicted prevailing theories. The Piltdown Man, announced in 1912 as a fossil link between apes and humans, was examined and described in scientific papers for over 4 decades before being exposed as a hoax in 1953. The fake fossil, combining a human skull with an orangutan jaw, fit expectations about human evolution better than the genuine fossils being discovered, which showed that brain expansion occurred late in human evolution rather than early as the Piltdown fossil suggested. Scientists saw what they expected to see and did not examine the evidence critically enough. The discovery of Homo floresiensis, popularly known as the Hobbit, on the island of Flores in Indonesia, was met with intense skepticism when announced in 2004. The fossils showed a tiny human relative standing only about 3.5 feet tall, living as recently as 50,000 years ago. Many scientists initially dismissed the find as pathological modern humans, with disease conditions causing small stature. Years of further research have confirmed that Homo floresiensis was indeed a separate species, showing that human evolution was more diverse and complex than previously thought. The initial rejection of the Hobbit discovery reflected assumptions that human evolution followed a linear path toward increasing brain size and body size, assumptions that the fossils contradicted. The timeline of human migration out of Africa has been repeatedly revised as new evidence has emerged. Each wave of discoveries pushes back the dates or reveals new migration routes, forcing revision of theories that had seemed well established. The presence of humans in the Americas was thought to date back about 13,000 years, coinciding with the Clovis culture, until older sites were discovered pushing the date back to at least 15,000 years, and possibly much earlier. Scientists were not lying about the earlier dates. They simply had not yet found the evidence that would force revision of their timelines. In physics, the concept of the luminiferous ether dominated thinking about light and electromagnetism for much of the 19th century. Scientists knew that light was a wave, but all known waves required a medium to travel through. Sound waves travel through air, water waves through water, so light waves must travel through some substance. This hypothetical substance was called the ether, and it supposedly filled all of space, allowing light to propagate from the sun and stars to Earth. The ether was thought to have peculiar properties. It had to be extremely rigid to support the high-speed oscillations of light waves, yet it also had to offer no resistance to the motion of planets and other objects, which passed through it without slowing down. Despite these contradictions, the ether theory was widely accepted because the alternative, that light could travel through empty vacuum, seemed impossible based on 19th century understanding of waves. The famous Michelson-Morley experiment in 1887 attempted to detect Earth's motion through the ether by measuring how the speed of light varied in different directions. The experiment found no variation, suggesting that either the ether was somehow moving along with the Earth, which seemed implausible, or that the fundamental assumptions behind the experiment were wrong. For years, scientists proposed increasingly complicated explanations to preserve the ether theory. The correct explanation came with Einstein's special theory of relativity in 1905, which showed that light did not need a medium and that its speed was constant in all reference frames. The ether simply did not exist. The reluctance to abandon the ether reveals how difficult it can be to let go of concepts that seem logically necessary. The ether made sense within the framework of 19th century physics. Abandoning it required accepting that light was fundamentally different from other waves, a conceptual leap that took decades to make even in the face of mounting evidence. Quantum mechanics, developed in the early 20th century, revealed that the classical physics that had seemed to completely describe reality was only an approximation valid at everyday scales. At the atomic and subatomic level, particles behave in ways that defy common sense, existing in multiple states simultaneously until measured, tunneling through barriers that classical physics says should be impenetrable, and affecting each other instantaneously across vast distances. These phenomena have been experimentally verified countless times, but they remain deeply counterintuitive. Einstein himself resisted some implications of quantum mechanics, particularly the probabilistic nature of quantum events and what he called spooky action at a distance. He believed that quantum mechanics must be incomplete, that there were hidden variables determining outcomes that only appeared random. Experiments testing Einstein's ideas have shown that quantum mechanics is correct, and that the universe really does contain fundamental randomness and non-locality. Even one of the greatest physicists in history was fooled by his intuitions about how nature should work. The expansion of the universe, discovered by Edwin Hubble in the late 1920s, came as a complete surprise to astronomers. Einstein's general theory of relativity actually predicted that the universe should be either expanding or contracting, but Einstein could not accept this and added a cosmological constant to his equations to keep the universe static. When Hubble showed that distant galaxies were receding from us, with more distant galaxies receding faster, Einstein reportedly called the cosmological constant his greatest blunder. The universe had fooled everyone, including Einstein, by being more dynamic than anyone expected. The subsequent discovery that the universe's expansion is accelerating, announced in 1998, was perhaps even more surprising. Astronomers expected the expansion to be slowing down due to gravity, but observations of distant supernovae showed the opposite. This acceleration implies the existence of dark energy, a mysterious component that makes up about 68% of the universe's total energy. Despite decades of research, the nature of dark energy remains unknown. The universe continues to hold secrets that challenge our understanding. Dark matter presents a similar mystery. Observations of galaxy rotation and gravitational lensing indicate that about 85% of the matter in the universe is invisible, interacting through gravity, but not emitting or absorbing light. Despite intensive searches, dark matter particles have not been directly detected. Scientists have been forced to accept the existence of this mysterious substance, based on its gravitational effects, even though its fundamental nature remains obscure. Future discoveries may reveal that current ideas about dark matter are as misguided as the ether theory, or they may confirm its existence while revealing properties no one has yet imagined. The history of science is filled with these stories of confusion, misdirection, and eventual clarity. Scientists are not infallible. They are human beings doing their best to understand a complex universe using imperfect tools and incomplete information. The scientific method provides a framework for correcting errors through observation and experiment. But progress can be slow, and wrong ideas can persist for generations. What distinguishes science from other ways of knowing is not that it avoids mistakes, but that it has mechanisms for eventually recognizing and correcting them. These cases of scientific confusion share common themes. Often, the truth is far stranger than expected, involving processes or scales that lie outside everyday experience. Sometimes, scientists are misled by observations that are accurate but incomplete, seeing only part of a phenomenon and making incorrect inferences about the whole. Theoretical frameworks that seem comprehensive and logical can persist even when evidence accumulates against them, because abandoning a framework requires not just accepting that it is wrong, but developing something better to replace it. Technology plays a crucial role in resolving scientific mysteries. Many of the confusions discussed here persisted because scientists lacked the tools to make critical observations. Microscopes were needed to see bacteria and barnacle larvae. Telescopes were needed to resolve distant stars in other galaxies. Seismographs were needed to probe Earth's interior. Particle accelerators were needed to test quantum mechanics. As technology advances, previously unobservable phenomena become accessible, often revealing that nature is more intricate than anyone suspected. The human element in science is also important. Scientists bring assumptions, expectations, and biases to their work. They may be reluctant to challenge respected authorities or abandon theories in which they have invested careers. Social and cultural factors influence which ideas are pursued and which are dismissed. Recognition often goes to those who make the final breakthrough rather than those who laid the groundwork. Understanding these human dimensions of science provides context for why errors persist and how they are eventually corrected. Looking forward, we can be confident that current scientific understanding contains errors that future generations will find obvious. Some of our most cherished theories may turn out to be wrong or incomplete. Questions that seem settled may be reopened by new evidence. Phenomena we cannot now imagine may be discovered. The universe has shown a remarkable capacity to surprise us, and there is no reason to think this will change. The key is maintaining humility and openness to new evidence, while still building on the accumulated knowledge of the past. Science progresses not despite its errors, but partly because of them. Each mistake, once recognized and corrected, teaches us something about how the universe works and about how we can more effectively investigate it. The story of science is not a straight line from ignorance to knowledge, but a winding path with many false starts, dead ends, and unexpected turns. These mysteries that fooled scientists for years remind us that observation is more difficult than it seems. Seeing is not the same as understanding. Interpreting what we see requires theoretical frameworks, and those frameworks can mislead us, even as they help us organize knowledge. The most important scientific discoveries often involve recognizing that our frameworks are wrong and having the courage to discard them in favor of better explanations. As we continue to investigate the natural world, we should expect to be surprised, confused, and occasionally fooled by nature's complexity. The scientists of the future will look back on our current understanding with the same mixture of respect for what we got right and amusement at what we got wrong. This is not a failure of the scientific enterprise, but its greatest strength: the ability to recognize error, learn from it, and move forward with better understanding. The mysteries that have fooled scientists throughout history are not embarrassments, but milestones marking the path of human curiosity and our endless quest to understand the universe we inhabit.